Not every problem requires that. There are harder problems that have a couple steps to them, and then there's easier ones like the one I gave you on the test. Because that was not a tell me, ask me. The area is pi r squared, take a derivative, throw stuff in, bam. You guys kind of with me? So when you do the homework, not every problem is going to be a tell me, ask me. Some of them are simpler. But I did the tell me, ask me thing to get you ready for the harder ones. Like the, do I still have that? Yes, I think I do. Like this one, remember this one? Yeah, so they told me the dimensions, and then they asked me for the volume of water. I've got to use those two together to get rid of a letter. You guys with me? Okay, maybe? You guys remember that? Okay. So, believe it or not, we did this problem. Here's all that beautiful work. And we did this problem. And we did this problem. Sweet. So now we just have number 3 left. Okay. So, I'm going to give you a second here. Does anyone remember? Well, first off, draw part A. That's easy. Do part A. That's just drawing and labeling. Now when you do this, you have a total dimensions of the tank, correct? You know, the good old standard conical tank that you see everywhere. Joke. All right. Where's my cone? Get in there. Ah! All right. Because it's conical.
What does that mean?
Conical means cone-shaped. So, plus I said, draw and label the cone. Okay. So try not to be too evil. You're right, because conical, I understand. You might not know, so that's why I said the cone. So of course, what's this here? Yeah, it's 20 feet. I know that. And what's this here? 60. So that's what they tell me. Now, choose anywhere in there for the water to be. Normally you put it like in the middle because you don't want to put it way down there. You want to put it at the top. So maybe the water's right here. That's the level of the water. Are you guys... Let me stop for a minute. So as I'm pouring more stuff into this conical tank, the level of the water is going to rise. But at any arbitrary time, I have no idea what the dimensions of the water itself are. Just know that they conform to the conical tank. I made a problem once. One of my students... Have you guys ever heard of the theory that cats are liquid? Nobody? What does liquid do? Doesn't it conform to the shape of any container you put it into? That's one of the most fundamental statements about liquid. And doesn't a cat basically do the same thing? So I made a problem about you pour a cat into something and you have to... Anyway, sorry. They said, we challenge you to make a problem involving cat as a liquid. And all right. So what the hell is this? Does anyone know? Because I could have put that anywhere I wanted to in the cone. So what is that? Do you know? Do you know what it is? I don't know what it is. So what do you call it? R, because it's the freaking radius. That much I know. I just don't know what number it is because it could have been anywhere in that cone. So it's just R, and that's going to change as I put more water in, right? Yes? Or H2O. And what's this? H. I love it. Kick ass. So you've introduced variables naturally because you have some unknown placement that you have to identify. Okay, this is why drawing a picture is a huge part of some of the problems. Not necessarily every single one, but some of them. Most of them, actually, I should say. Now, what do you guys notice? Now, the next thing I'm going to ask you is find an expression for the volume of water in the tank. Well, that one really is just, all right, this is where, does anyone know what the volume of a cone-shaped thing is?
1/3 h pi r squared.
Yes. So a cylinder is circle times height, so pi r squared times height. If you chop a cone out of it, you actually leave 2/3, you cut 2/3 off, so what's left is 1/3 of the original. That is actually, all right, stay. That is actually true for any pyramid shape. A cone is the simplest pyramid shape. Because all a pyramid is, it goes from one point on the opposite side to all points on the other side. So watch. Why am I doing? Just because. Ha ha ha. Where do I have room? I have room here. All right. Real quick. Sorry. Oh, that's disgusting. Who cares? All right. There's my box somebody sat on. Poor little thing. Now watch this. If I take every corner and go to a single spot on the top, even with my crappy ass drawing, doesn't that look like a pyramid in there? Even with my terrible drawing, that's a pyramid. So what is the volume of the pyramid going to be? 1/3 the volume of the container it was cut out from. So 1/3 length times width times height. So in this case, do you guys have to remember this? No, I'm just giving it to you in case anybody enjoys math out there and didn't know this. So a cone is cut out from a cylinder, so it's going to work the same way. The volume of the cylinder, 1/3 of that is what the cone would have if you chopped off all the outside. Okay, I like it. So find an expression for the volume of water in the tank. It's just going to be this, because now we've identified R is the radius and H is the height. Those are really good choices. Now, can we find a relationship between the radius and the height? Say again? The height is
3 times the radius.
Yeah, so let's all catch up. So he said the height is 3 times the radius. Does anyone see where that came from? The original numbers, but you really, honestly, in general, you don't want to just go 60 divided by 20, so 3. That's basically is what happens, but don't you have similar triangles here? Isn't R to H equal to 20 to 60? Which is 1/3, so if you multiply that up, you get H equals 3R. So that constantly remains the same as the water, I'm pouring it in, so as the water level goes up, that relationship is true. Which again kind of makes sense, because aren't the sides linear? So that's why it's a linear relationship between the height and the radius. All right, let me stop for a minute. Didn't we do a problem that had this same thing? Similar triangles? You guys, that happens a lot. Not every problem, but similar triangles comes into play in a lot of these problems. So now we've got, come down here, H equals 3R. So now, of course, I can write my volume as a function of radius only. So this is a tell me, ask me situation. They tell me H is 3R. I'm going to ask you something about the volume. So now I can use what they told me in what they asked me. So how do I rewrite the volume? Well, in place of H, I can just put 3R. That is not generally true. That is true for this cone. Because another cone could be fatter or skinnier or whatever. Okay. I really want you guys with me. Nobody's asking questions. I'm hoping. Yes?
You said it's not always 1/3 or all of it?
This cone, this is true. I could have a different cone that's fatter or skinnier. That would have a different relationship. Okay, good. So I want to be careful. You can't suddenly say this volume formula always becomes what we're going to get here, because this is only true for this cone. Okay. The mood is about where it should be, I think. Okay. Because this is not easy. It isn't. Not at first. So if you feel a little bit confused, ask questions, but understand this is about where you should be with these problems. It takes practice just like anything. So what do I get here, of course? This becomes really nice. Yeah, freaking pi r cubed. That's awesome. For this cone. So now I know, let me just put this together. Now I know the volume is pi r cubed. What did I tell you the very beginning of the problem now? What did I tell you the very beginning of the problem? Water is oh, it is draining, Jeff. Okay. So somebody shot a hole in the bottom of my tank. Water is draining at this rate. You guys with me? So what is that? How am I going to represent this in symbols? Oops, sorry. How am I going to represent this in symbols? Yeah, it's the change in volume over time, right? How do you know that? It's freaking volume. Where'd it go? Volume over time. There. That's so kick-ass. So that is why the dy dx kind of symbol is better when you really want to know what your units are and so forth. Or there's a beautiful connection. The y prime ain't got that. Right? It's as bad as my grammar. Yeah. Ain't got that. So I know that dv dt is this freaky ass 48, what is it? 48 pi. I don't care about the units right now because I'm going to deal with math. And what's it asking me for? Say again, sir? dr dt. It's asking me for that. That's the question. So, of course, and it also tells me r equals 16. That's the snapshot. So water's draining out. I want to know right at the moment when the radius is 16, I want to know how quickly the radius is changing. Would you all agree with me that as it goes down, the radius change is going to be different? Maybe? Okay, maybe. Okay. What do you do from there? Yeah, because I've got all this information and they're asking me questions about rates of change and I don't have any relationship between the rates of change. So what do I get when I take this derivative? I'll do this side. Okay, I did my half. That's not funny, Jeff. All right. Sorry?
3 pi r squared.
So far so good?
dr dt.
dr dt. Remember, it's a chain rule. I'm not taking it with respect to r. Taking with respect to t and what's changing over time, volume and radius. So I really want, all right. Even though this section is in our past, I know that we're not all comfortable with implicit differentiation. Is that a correct? Like, even if you're okay with it, are you really comfortable with it? Anybody? It would be great if you were. You just don't want to tell me. This is implicit because these are both implicit functions of time. Do you see any explicit reference to time? Do you see t in there? No. So when I take derivatives, it's got to be chain rule. Because r is a function of time, so you take the derivative of the outside function, bam, and then times the derivative of the inside function, okay. And what kind of makes sense there is, now you got, if you didn't have this, how the hell are you going to answer a question about it? That should be a huge red flag, right? How are you going to solve for this if you ain't got it? All right, so go ahead and finish that up. The rest of it should be semi-simple. Oh, you already, we'll catch it. Very curious. If anybody can get the exact answer, let me know. All right, that's this. Okay, that's still those are acceptable, but I haven't heard the exact answer yet.
Feet over seconds, I think. No, cubic feet over seconds.
Not the. I don't care about the units right now. I will care about the units in a minute, but I'm just worried. All right, it's 1/16. Why? How many 16? Just stay with me. How many 16s do I have here? 2 of them, right? What's 3 times 1 of the 16s? All right, so that cancels with that. Don't the pi's cancel? Then I would divide by 16. That would be the answer. Okay, so it's 1/16. Now, would I require that from you? No, I'd tell you to round it to whatever, but you know. So let me stop for a minute. Yes. Yeah. Okay. Let me. Here. So we had this. Let me write this like this. Is that cool? Isn't 3 times 16 equal to 48? So don't those cancel? Don't the pi's cancel? And then how do I solve for this? I divide by 16. All right, so there's a 1 left here. Divide by 16, so it's 1/16, yeah. But if you get what is it, 0.06? 0625? Okay. So then you're right. Whoever said that. So drdt equals 1/16. Now what's the units? Yeah, feet per second. I like it. So the radius, if I wait a second, it should be roughly 1/16 less than it was before. Right? Why won't it be exactly equal to 1/16? If I wait 1 second, this result is saying it should be 1/16 less. Yes? So why is it not exactly 1/16 less? Yes, this is the change in radius at that point in time. The minute I let any time go by, that changes. But it's a good approximation. I love this. How fast is the height? Now this is neat, okay. By the way, real quick, one little thing here. Everything here is about losing water, correct? So I just said everything is losing water. Technically, what should this be? It should technically be negative, yes? So you could put an explicit negative in. If anybody's taken any physics, you know that negatives and so forth are really important, but I can define one direction to be positive and the other direction to be negative. Anyway, sorry, little thing. Okay. What about this shit here? Why could I do this problem? Did I have a relationship between radius and volume? I really want this to make sense. I had a relationship between radius and volume, therefore, derivatives, I have a relationship between change in volume and change in radius. Yes? So look at what is that? F. How fast is the height dropping at the instant the radius is 16 feet? What do I wish I had a relationship between then? Height and radius.
Which we have.
Do we have that?
Yeah.
Yeah, we do. Don't we know this? So then height is 3 radius. So what's the relationship between the rates of change of those? Yeah, and do we know what this is? Yeah, we do. At this point, right? So we just got to throw that shit in there. Okay. I love that problem. Sorry. Good for you, Jeff. Okay. Yes.
So the answer to part B would have been 1 is positive.
No, not really. I mean, as long as you said decreasing, yeah. Again, it is just like physics. You could define one direction positive, one direction negative, as long as you're consistent with your definitions, you're fine. So you could put a negative there, or you could just know that it's a loss throughout, right? It's a little bit, technically you want to get used to doing this, putting a negative in there, because part could be negative and part could be positive. So I could have said it's draining out at a certain rate and somebody's pouring in some at a certain rate. Then you have to have different signs for both. Okay, maybe. And it just makes sense then to call the amount coming out as negative, because that's a loss. I love you guys so much. Does that make any sense? If you're losing something over time, you should go ahead and make it a negative. If you're gaining something over time, you should go ahead and make it a positive. Okay, just in case you have two things at once happening. This problem, it's all a loss, so it almost doesn't matter. Okay. This is an example of kind of a medium hard problem. Okay. So you have to get into section 3.9. I think some of you guys have done some of 3.9. Yes?
Is 3.9 going to be on the next test too?
Yes. Slightly more difficult problem. 3.9 will be on the next test. Wait, what's that? No, sorry. That's all you. Okay. All right. Oh, cool. All right. So now we're going to do 310. And then we're going to call it a day. And of course, I did not bring much paper with me, as per the usual. Okay. 3.9 is normally one of the harder kind of early sections in calculus. Students normally, you guys normally pick up on the derivative rules and so forth pretty well. You make little mistakes with them, but you pick them up pretty well. 3.9 is funky because everybody has this dislike of word problems kind of baked in, right? Is that a true statement I can make?
1000%.
And 3.9 is our first foray into calculus word problems, which you kind of have an immediate bias against, which I understand. So 3.10 is going to feel a little bit better. Let's find out if that's true. We're going to talk about some stuff that we've talked about before. I've sort of been trying to get you ready for this before. So let me 310 is all about linear approximations and differentials. Okay, right? Linear approximation we've done before. I just didn't call them a linear approximation. So what is true if I have a function and I find a derivative at a point and I get the tangent line? What must be true about that tangent line? Like, I've drawn this tangent line horribly, but close to that point, the tangent line and the original function have to be close, yes? In fact, if I zoom in on the square root function, it's going to become more and more linear as I look closer, right? Okay, that's the idea of local linearity. If I zoom in on any function, it's going to look close. It's sort of like we live on a globe. Because we see it up close, it looks flat to us, right? Some people extend that a little too far, but oh, okay. So let's look at this idea, and it's really the same idea as a tangent line. That's what a linear approximation to a function is basically the tangent line built around a certain point. So would this approximation here work really well for inputs out here? That tangent line would suck, because at that point, isn't it way the shit up here? So this would be the approximation, and this is the actual answer. Depends on what it's good enough for government work, but is that really a good approximation? No, that's off by quite a bit. Okay, so part of the problems in the section are going to involve how far can you get away from that point and still have a good enough approximation within some error tolerance. Oh, Jesus. So I want my approximate answer on the tangent line to be within so much of the actual answer. Okay, all right. So let's do an actual, let's remember how this works. How do I find the tangent line to a point? Don't I have to know a point and the slope, right? Okay, let's take it way back. So isn't this, how does this go? Y minus y1 equals? Okay, so let's replace that with some more higher level shit, right? So let's say that this point is A. That's crazy. So I want to build, I really want this to make sense. This tangent line works really well for values close to A. Yes? That is when that line is really close to that curve. It's for things close to, in fact, right at freaking A, don't they agree completely? Because that's where it hits. I really want this to make sense. Where's that tangent line hit the curve? At A. So if I don't get too far away from A, I could use the line to get outputs for the function. And when is this going to be really useful? If my function is freaky as shit. It's much easier to throw a number into a linear equation than it is to throw it into whatever we've seen, right? Okay, stay with me. So what is this actually? If the input is A, so let me put that in there. What is this? What's the output? F of A. Okay, so this is y minus f of A. And what's m? Related to f of x and a and all this shit? Say again? F prime of A. There it is. All right. We've actually not done anything new. This is just what we did for tangent lines, just spelled out more generally, right? Well, how do you find the tangent line? Did you find the slope at the point? And then just plug the point in and get the line? Isn't that just what that's saying? That's just what that's saying. So therefore, I know this. Okay, that's amazing. So this is called the linear approximation. Okay, let's do an example. Okay, believe it or not, we've gotten a result. That is the result. So what if my function, all right, let's do the function I basically have up there. What if my function is square root of x, and I want to build a tangent line around, let's do this. Sorry, let's do something like square root of x plus 1. That's right. Let's do this. Okay. And I want to build it around a equal to 0. So all right. Part of me hates that we do all this, to be honest, because all I'm asking you to do is to find the equation of the tangent line to this function at the point. That's all I'm asking you to do. And we've done that before, correct? We've done that before, correct? Yes. That's all this captures, but I want you to get used to this setup because it leads into Calc 2. Even if you're not going to take Calc 2, I don't care. It still leads into Calc 2. Okay, so what do I need? I need to know what f of a is. So what is f of a? That would be f of 0, yes? Which is? Holy shit. So I got f of a, check. I need to know f prime at a. So how do I do that? Find the derivative. So the function is this. So go ahead and find the derivative. Don't say anything. Try to figure out what f prime at 0 is. All right, what do you guys get? Beautiful. This looks terrible, right? But then when you plug a 0, it's just 1 to a power. Who cares? So now I know everything I need to know. So I know that y equals f of 0 plus f prime of 0 times x minus 0. So y equals f of 0, which is 1, plus f prime of 0 times x. Therefore, the square root of x plus 1 is approximately 1 plus 1/2 x for x close to 0.
Minus f prime 0?
Say what? Sorry?
Is it f prime 0 or 0?
Say one more time, sorry.
Is it f minus f prime 0 or is it plus f prime?
F. All right, where are we talking about?
So in y equals f of 0 plus f prime 0?
Here.
Plus or minus?
Here?
Yeah.
Okay.
It's always plus.
Plus. Here?
Yeah.
That's a plus.
Okay.
Yes.
Oh no, I know. Okay. Never mind.
I'm sorry. I really don't understand.
It's okay.
All right. Now, let's test this out. Let's test this out. So let me write this down. Let's see what we've got so far. So we got 4 f of x equal to square root of x plus 1. With x close to 0, f of x is approximately equal to 1 plus 1/2 x. Okay. That's what we just figured out. So can we approximate? Let's see if you guys get this. The square root of 1.1. Will I put a 1.1 here? What's the function? Square root of x plus 1. If I want to know the square root of 1.1, what's x? 0.1. Kick ass. So put a 0.1 there. Does everybody see that?
No.
What's the function? What's the function? Square root of x plus 1. So if I want to approximate square root of 1.1, what must x be? 0.1. Does everybody see that? So x is not just the number they give you. You got to base it off what the function is. If the function is 1 plus x and a square root, if I want to know square root of 1.1, x must be 0.1. Does everybody really see that? Okay. So what do I get for the approximation? Become a thing. Yeah, 1 plus 0.5 times 0.1 is 0.05, so 1.05. Is everybody cool with that? Can somebody please just do this in your calculator? Let's see. So this is our approximation. Was that hard to do? If I ask you what is this and I say do this by hand, could you do that easily? Yeah? Okay. No, you could not. Now you can. You can get an approximation. How good is the approximation?
It's okay. Pretty good.
You guys have high standards. Isn't it 1.048 something or 888? Blah, 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 blah. Okay. Which for most humans is 1.05. Now, So most of you agree that's pretty close. If you were working with like machining little parts for something, and if there was any error, then it would like wiggle and cause friction and your whole machine would die. Do you think that might be an allowable error? Maybe not. Okay. So depending on what you're using this for, the allowable error will change. How big of an error is this? About?
It's a small error.
Small error. Well, what is it about? 0.0012 roughly.
Depends what units you're working in, I guess. What if you're working in thousands of miles?
Yeah, it also has to deal with error propagation, right? If you're going to then multiply this by, I think that's what you're thinking about, right?
Yeah.
Yeah, so tolerance could either be the thing you're looking at directly, or it could be what are you going to use this value to do next, right? Because if you multiply it by 1,000,000, you are off by a lot. Okay, I like that. Good point. Is everybody with me? Does that make sense? I mean, that's obviously how far off we got with our estimate. Yes?
I'm just a little confused what we're doing and why.
All right. I really want you to understand what we just did. I want you to understand what we just did. If I asked you before today, what's the square root of 1.1, you cannot use your calculator. You could have guessed, right? You could have guessed something. And you could pretend to yourself you would have guessed 1.05. Maybe some of you would have, but who knows what the guess would have been. Which function is better? The square root of 1 plus x or 1 plus 1/2 x? Which one's just easier to work with?
1 plus 1/2 x.
Yeah, isn't 1 plus 1/2 x a much better function if I have to do things by hand than the square root of x plus 1? Isn't that a much better function? Yes. Then you have to play that off. Where does it work well? For values of x close to 0, right? That's what we built it around. So what if I wanted it to work well for values of x close to 3? Wouldn't I go start at the beginning again? Let a be 3. Do you guys understand? Do you want to try to do that now? Or no? Yes? Okay, no? Yes? Okay, let's try it. No? You're good, okay. All right. Let's do a different function. What time we got? Oh, we got time. Oh, you guys are having so much fun today, I can tell. Oh yeah, let's do this one. Okay. Sorry. I'll calm down. You guys are all like, I hate this shit, and it makes it worse that you love it. I'm sorry. Is it really worse? Would it be worse if I hated it too? All right. So what if I had this function? All right, let me not do that to you. Let's just stick with f. That's fine. It's a totally different problem. We can just use f. So to figure out, and let's do for x is close to 0. Sure. Okay, so what do I need? I know that my approximation is this, which is the same old function from algebra. We just replaced m with the derivative, right? All right. Try to see how far you can get to piece that together. A is 0, correct? A is the input you want to be close to. See how far you can get with that. This will be a very familiar result. Let's see if you guys agree with me.
Is this actually I'm doing it wrong if
Yeah, dude. So I need to know, so let me put this more specifically for us. Right, if A is 0. So I need to know what f of 0 is. Well, what's f of 0? 0. I need to know what f prime of 0 is, so what's f prime of x? So what's f prime of 0? 1. So if I plug everything in, I get y equals 0 plus 1 times x. Why is this not surprising? Do you guys remember what this was? Isn't that 1? Doesn't that mean that these become the same as you get closer to 0? Isn't that what that means? If the limit of the ratio is 1, that must mean they become the same number the closer you get to 0, which means sine x is approximately x close to 0. And isn't that what we just figured out? The linear function that best approximates the outputs for sine x for inputs close to 0 is y equals x.
Wouldn't cosine x be the same thing with a slight multiplication? Or an addition, right? Like,
Yeah,
yeah.
but cosine of 0 would be 1, so you'd have a 1 plus,
Yeah, okay.
and that gets really weird because the slope, what's the derivative of cosine of sine? What's sine of 0? 0. So there'd be no slope. So it'd just be the approximation for cosine close to 0 is 1, just the flat line 1. Because think about it, doesn't cosine look like this? I don't know if you guys.
It has no slope at that point.
Isn't this exactly?
Yeah.
See how it all comes together? It all comes together. It does. I don't know if you guys are with me. Right there, just by looking at the graph, I would estimate that this has to be a horizontal line that approximates this the best. That's the tangent line of cosine of 0. And sure enough, your best guess, what's the cosine of 0.03? 1. That's my best guess. Because cosine of 0 is 1. So cosine of 0.03 is 1. That's the best guess. That's a great guess. What's the cosine of 0.03? Make sure you're in radians. Somebody help me out. What's the cosine of 0.03? Say it again, sorry. 0.99? Not, okay. All right. Okay, really, and again, that's why, okay, part of me wishes I would just teach this and say, we've done this shit, just find the tangent line. We've done find the tangent line. We've done it. Just find the tangent line. That's really all we're doing. We're just doing it in a little more prescribed way, and there's a reason for that. We want this kind of understood, because what I really want you to understand, isn't this is the actual answer, yes? At 0. This piece would be the actual output of the function, yes? This is an adjustment if I move a little bit away from 0. That's an adjustment, the first derivative adjustment. In Calculus 2, how many of you guys are going to take Calc 2? How many of you guys thought you were going to take Calc 2 until you had me and you're like, I don't want to. Okay, I'm sorry. I'll be all right. You turned me off to math. Okay. In Calc 2, you add more terms, second derivative, third derivative. Because what this is saying is, I'm trying to take a curvy function and approximate it with a line. Wouldn't it be better to approximate a curvy function with another curvy function?
Yeah.
So there's another thing I could do where it's f double prime of a over 2 times x minus a squared. So that would be a quadratic fit. A quadratic approximation. Wouldn't that fit better? At least locally? All right, I'm sorry. I went too far. I'm sorry. But again, I just want to let you know there's a reason why I'm making it feel like it's hard. I'm not trying to make it feel like it's hard. All we're freaking doing is finding the tangent line. That's all this says, but it just looks different. Okay, maybe. Now, last thing we're going to do. What if, so let me do this on this page. Oh, well, let's do this. I forgot to do a specific example. So we've got 2 more things to do. Can somebody approximate sine of 0.03? Sure. Oh, yeah, there you go. I was waiting to see if anybody. And what is sine of 0.03? Why is this true? Because the approximation to sine is x. right? So for x is close to 0, the output will be the input, which is neat. What is sine of 0.03? 0.02995 stuff, whatever. Okay, which is basically 0.03 for most humans. Okay. Humans. Yes.
Can you explain why again?
Why what?
Why it's the same point of view?
We just found this, right?
Oh.
So close to 0, this function looks like this. And let's check it out. All right, let me do something on paper, then we'll do something on Desmos. Oh shit, damn it. Well, let's do this. All right, so we'll do that next time. Let me at least show you this. I think I have 10 minutes, don't I? I always feel like you guys like, no, Jeff, you're out of time. Shut up. All right, let me try to squeeze this in. If I want it to be, so our approximation is this. And I want to know, how long is that good, right? So what if our error tolerance, oh geez, was 0.1? Like we want the result to be within 0.1. So this result, that wascally weapon, this result right here is good, isn't it? Isn't that within 0.01? I'm sorry, what did I say? 0.1? It's within, it's definitely within 0.1. It's within 0.0000. Holy shit. So I'm curious, how big could I let that input be? And the error would be less than 0.1. That's the question. Does that make sense?
2.
Say again?
2.
Where'd they come from?
I plugged something in on my calculator.
All right.
Actually, I don't even know if it's.
I like it. Do we want to do guess and check for everything? Because that could lead to an infinite amount of guesses and checks. Okay, so, real quick. I want, now let's see if you guys agree with me. I want the error tolerance to be 0.1. So don't I want the difference between these to be less than 0.1? It's debating on whether to put an equal to. I can't remember what this book does, but normally put a strict less than. Stay with me now. Do you guys all agree with me? Isn't that capturing the idea mathematically? I want the difference between those two functions to be less than 0.1. Okay, which means, please tell me everybody knows how to rewrite absolute value inequality, right? Then I can add x. Okay. I want that to be true. Is everybody, nothing too crazy there? Nothing too crazy? And you're all like, everything's crazy here, man. It should feel a little familiar. I'm going to change this over. Everybody ready? Everybody got that? Okay, I'm going to change this over. Jeff. Jeff, okay. So much shit up here. There. All right. So if we put in here, what do we got? X minus 0.1 sine x, x plus 0.1, Jeff. All right, I want you guys to see. This should feel a little familiar. I don't want to tell you what it should feel familiar with respect to, because you guys would. Oh, do you definitely out here? My approximation sucks.
Yeah.
The error would be huge. So again, right down the middle. Let me put in here. Here's my approximation. Let me do this. All right, approximation was x. Jeff, would you all agree that kind of sucks that it's purple, but oh well. It does a really good. Look how good of a job it does. Shit. Can you tell the difference between x and sine x in here? If I zoomed in, you can start to see, right? But good Lord, I got to zoom in a lot. That's the basic idea of this whole thing. really close to 0, the function is pretty much linear. So the error should be pretty small in here for damn sure. And then as I move out, you can start to see the error visually here. So that is really bad out there. Okay, now, so if I come back to this, when is my approximation within 0.1 off? Do you guys see down here? When does it start to be good? Right there, yes? And of course, it's good all the way in here. Look, this means that my approximation would be within 0.1 of the actual function. That's what this means. So when do I start to be bad again? There. So can't I just find those intersections? So it's good, but from, no, give it to me. Is that what I want?
Yeah.
There it is, okay. Negative 0.85 up to positive 0.85. Which makes sense because sine is symmetric, so boogie woogie. So between negative 0.85 roughly and positive 0.85, those inputs will be within 0.1 of the actual answer if you use the approximation. Further than that, it gets worse, right? So if I make my approximation, if I wanted to be better, now it gets really difficult to find, but I can see it enters right there. Now I got to be negative 0.39. Come on, you can do it. Up to 0.39. Yeah. So then it's got to be a lot closer to be within so much. Doesn't this feel a little bit like epsilon delta? Oh shit! See, I didn't want to say that earlier because a lot of you guys would have just went, screw this shit. But this is a lot easier than epsilon delta, but it kind of feels like it. Okay, that's enough. That's enough. I've tortured you plenty. Let me know if you guys have any questions about anything. Yes.
So what?